In this video, we are going to look at the basic thermal circulation. The most common example of a thermal circulation is the sea breeze, and its opposite, the land breeze. But there are other types of thermal circulations, such as mountain and valley breezes as well. So let's start off by learning about what causes this thermal circulation. First of all, let's assume you have an area where everything, the temperature is equal, pressure is equal, everything is uniform. Then in the south, let's say that the sun heats up the air a little bit more and the air in the north gets cooled. As a result, in the south, because the warmer air is expanding, that causes the isobars to rise. In the north, where it's cooler, the isobars compress, and so they get decrease in altitude. As a result, your pressure at a given height over the southern area will be slightly higher than the pressure at the same height over the north area. And so you have a difference in pressures, higher pressure at a given altitude in the south to low pressure at the same altitude in the north. This creates, of course, a pressure gradient force, drives wind. But if you have air moving over here into the north, that increases the total amount of air, which will thus increase the total pressure at the surface. And with air leaving the south, that means there's less air, so that will decrease the net pressure in the south. And so as a result, you get high in the north, the surface, low in the south at the surface, air flowing the opposite direction. So then you end up having a circulation pattern as shown here. Now this is the basic thermal circulation. It's a circulation pattern based solely on difference in heating. A good example of this, if you're walking in a city and you walk by an alleyway, you feel a breeze coming out of that alleyway. Why? Because out in the street in the sun, the air is heating up and warming up, rising, but back in the shadows, the air is cooling down and sinking. You end up with a thermal circulation through the alleyways between large buildings in cities. Okay, that's just a simple example. A much larger, more complicated example is the sea breeze, where exactly the same thing happens. Because the difference in heating rates of the land and the water, the land is going to heat up faster, so you end up with a high pressure aloft. The water is going to heat up slower, so you're going to end up with a low pressure aloft, creating a wind circulation that follows this very pattern here. This is your sea breeze. But what happens at night? Well, at night, land heats up, in day, the land heats up faster than the water. So at night, the land also cools faster than water. So since it cools, it's going to be colder than over the water. Your high pressure is now over the water. The entire wind pattern reverses. So when you live in an area where there's a sea breeze, you'll typically see lots of cloud formations over the land. And if the sea breeze is strong enough, you'll see thunderstorms, pretty severe thunderstorms at times. And then at night, those thunderstorms will disappear and you'll start seeing thunderstorms over the water. All right, now here in Florida, we have a very unique situation. Here in Daytona Beach, we have a sea breeze that's coming from the east, from the Atlantic Ocean. But across the state, over in Tampa, they get a sea breeze coming from the west, from the Gulf of Mexico. Okay, great. So we each have our own sea breeze. But in the summer, when it gets hot enough, these sea breezes get so strong that they reach the center of the state. And when they reach the center of the state, they converge, hit each other. There's nowhere else to go but up. And so they form some even larger, stronger thunderstorms right down the center of Florida. This region is what we call the sea breeze convergence zone. And being from Daytona Beach area, we have looked off in the direction of Orlando, off to the west many times, and seen scenes like this where we have very, very large cloud structures with very intense rain underneath them in the middle of the summer. This would be the line of the sea breeze convergence zone. So in summary, a sea breeze comes from the uneven heating of land and water. During the day, the land is hot, the water is cold, and so that would constitute your sea breeze. But at night, the water is hot, the land is cold, that would give you a land breeze. Now, the local winds are always going to change in speed and direction as they cross large bodies of water. This has to do with the fact that water has less friction. And when you have less friction, that means they get faster wind speeds and you have faster Coriolis effect. So you can also get changes in not just the speed due to less friction, but changes in wind direction due to the greater Coriolis effect. Here's another good example of a thermal circulation, the valley breeze and the mountain breeze. As the sun rises over a valley, it heats up the air in the valley quite well because there is a lot of land. But at the top of the mountains, there's only the mountain itself. There isn't as much. And so it tends to be a little bit cooler at the top of a mountain, but warmer in the valley. So in the middle of the day, the hotter, warmer air from the valley then rises to the top of a mountain and creates a cloud line right over the mountain edges. Gives you a scene that looks something like this. But at night, the opposite happens. The valley cools faster than the mountain does, and so the air that had been up at the top of the mountain, now that it's a little bit cooler, starts to sink and settle down into the valley. The rising air in the daytime is called the valley breeze because it comes from a valley, and the sinking air from the top of the mountains is called a mountain breeze as it comes from the mountain.